Hello friends, in the previous lecture we discussed the zone method. Zone method is basically an extension of net radiation method, where in net radiation method we used the view factors and we applied the energy balance on surfaces. In zone method we use direct exchange areas and total exchange areas, and we apply the energy balance to surface zones and gas zones. So, the domain of the problem is divided into a number of surfaces, we call them surface zones, and the volume is divided into a number of sub volumes and we call them volume zones. The direct exchange area is analogous to view factor, with an advantage that here we have incorporated the participating media. That means the effect of absorption and scattering is included in the definition of the direct exchange areas. In today's lecture we will see how to calculate these direct exchange areas for some simplified geometry. For complicated geometry we may have to go for statistical methods like Monte Carlo or some higher order numerical integration scheme. So, let us see, before we start I will summarize the governing equation of the zone method. So, in the zone method we have a domain of interest which is divided into surface zones and volume zones. So, this is the volume zone and we have a number of surface zones. So, this is typically what we do in computational fluid dynamics, we divide the domain into finite volumes. So, here the domain is divided into finite volumes and we have surface zones and volume zones. Volume zones are also called gas zones. We have total ns number of surface zones and n subscript g number of gas zones. So, the total number of equations that we get is ns plus ng for total unknowns ns plus ng. So, ns plus ng is the number of equations and ns plus ng is the number of unknowns, and the variables here in the zone method are the total absorption at the boundaries, that is h underscore h subscript s, that is the total absorption at the boundary, and hg which is total absorption at the volume. So, g is the incident radiation and kappa times g basically gives you the absorption of radiative energy in a gas or volume zone, and hs is surface irradiation, which multiplied by emittance or absorptance gives you total absorption at the surface. So, with these variables we have total ns plus ng number of equations, and the equations are basically given here. So, we have total 1 to ns number of equations and total ng equations 1 to ng equations from here. So, total ns plus ng equations in hsj and hsg. So, this represents a system of linear equations which can be solved using standard techniques for solving linear equations. The unknowns here are hsj and hg, but before we have to solve for this we have to find out the matrix that basically governs this system of equation, and the matrix depends on number of variables like direct exchange areas from surface to surface Si Sj. It depends on surface to volume direct exchange areas Sij, and it also depends on volume to volume direct exchange areas Gij. So, these variables, these parameters need to be evaluated before we apply the system of linear equation solver to find out unknown variables hs and hg. So, how do we define these variables? So, surface to surface direct exchange areas is defined basically as total energy coming from a surface zone and directly travelling to another surface zone. Now, this energy that is directly travelling without any reflection from the surface, without any scattering in the volume, it directly travels from one surface to another, but when it travels from one surface to another it may be subjected to absorption. So, the view factor or the direct exchange area between the two surfaces I and j may be defined as double integration e power minus beta s cos theta I cos theta j divided by pi s square daj dai. This is the normal definition of view factor. The thing that we have multiplied with is the transmittance or transmissivity of the gas. So, let us say we have two surfaces, this is aj and this surface is ai, and we are interested in finding the direct exchange areas between these two surfaces. So, we have to double integrate over these two surfaces. The medium between these two surfaces have extinction coefficient beta. So, beta is the extinction coefficient between these two surfaces. So, when radiation travels from one surface to another, it will be subjected to attenuation, and there is an exponential term that basically comes into the definition of direct exchange area. Of course, this evaluation of this exchange area is not trivial. We have seen that even for medium or plates bounded by vacuum, when there is no medium, the evaluation of this double integral, whether with the double integration method or contour integration method, is very difficult. And when we have exponential term in this integral, the evaluation is going to be very difficult. We will see some simplified geometry and see how we can evaluate this, but the expression that we have obtained for surface to surface direct exchange area is difficult to evaluate, and normally we apply Monte Carlo methods for the evaluation of this direct exchange area. The direct exchange areas evaluated in this fashion follow the reciprocity Si Sj is equal to Sj Si. That means direct exchange area from surface I to surface j is same as direct exchange area from surface j to surface I. In a similar fashion, we define volume to surface direct exchange area or surface to volume direct exchange area. So, we have a surface and we have a volume zone, and let us call this is volume zone I and this is the surface zone j, and we are interested in finding the exchange area between these two. So, Gi Sj, that is direct exchange area between surface volume I and surface j, is defined as total energy coming from a volume and directly travelling to surface zone. Now, this energy will be subjected to attenuation as we discussed for surface to surface exchange, but this energy will not be subjected to reflection and in scattering. So, we are basically interested in direct travel, and in scattering and reflection is not taken into this. The scattering will attenuate the radiation, so that is accounted, absorption by attenuation by absorption and scattering is accounted, but augmentation is not accounted. So, we are interested in direct travel. So, the definition of this exchange area by similar terminology is given by a double integral. Now, one integration is over the entire surface j and one integral is over the entire volume I. So, we have this double integral e to the power minus beta s, where s is the path length, beta is extinction coefficient, cos theta j pi s square beta I daj dvi, where beta I is now the extinction coefficient in the volume. So, extinction coefficient in the volume appears in this integral because we are interested in how much energy is emitted from the volume. So, energy emitted within the volume is proportional to the extinction coefficient within the volume. So, we have now two variables beta I and e to the power minus beta s appearing in this integral. Beta I is a local variable that is inside the volume, while beta depends on the path. So, beta will vary from the location of I to the location of j continuously over the path. Again, this is going to be very difficult to evaluate, but we will simplify this for simple geometries. The volume to surface exchange area also follows the reciprocity rule, that is Gi Sj, volume to surface direct exchange area is equal to surface to volume direct exchange area Sj Gi. Finally, we also define volume to volume direct exchange area. So, we have two volumes, this is volume I and another volume in space volume j. The extinction coefficient here is beta I, extinction coefficient here is beta j, and we are interested in the direct exchange area between these two volumes and over the path the extinction coefficient beta will vary. So, we define total direct exchange area between these two volumes as the energy coming from a volume zone and directly travelling without reflection and scattering to another volume zone. This radiation may be subjected to attenuation by gas over the entire path length S. Okay. So, we define GIGJ, where is GIGJ is the direct exchange area between two volume zones I and J. Its double integral over the two volumes Vi and Vj, and now what we see here is that we have two beta I and beta j appearing in this integral, where beta I beta j are local extinction coefficient. We have double integral over the volumes, and E minus beta s is the attenuation over the entire path. Again this is going to be evaluated in a difficult way, but we have this reciprocity, and this reciprocity between two volume zones GIGJ is equal to GJ GI says that the direct exchange areas between two volumes is also following the reciprocity rule. Now, we have some additional rules, just like the view factor, we have rule of summation of all view factors from a surface is equal to 1. We also have summation rule for direct exchange areas. So, we have from a surface, so this is for surface I. So, for surface I total energy is conserved. So, total amount of energy emitted from this surface I is either going to other surfaces surrounding this surface I. So, summation over all the surfaces j. So, summation j Sj Si, or this energy will be absorbed by the gas. So, we have summation j Gj Si, and this should be equal to total amount of the exchange area, which is equal to Ai. So, this is same thing that we did for the view factors. So, total exchange area from the surface I should be equal to its area Ai. Similarly, for volume I, the energy is conserved. Total amount of energy emitted from a volume is basically equal to 4 times kappa I plus sigma I, where kappa I is and sigma I is nothing but beta I, the extinction coefficient, times its volume Vi. So, the total amount of energy emitted from the surface will be proportional to 4 times V times the extinction coefficient, and this should be equal to the sum of exchange areas between volume and surface. So, all the energy emitted from the volume will either be absorbed at the surfaces J, or it will be absorbed by other volumes. So, we have to integrate or sum over all the volumes. So, summation Sj Gi, summation Gj Gi should be equal to 4 times beta I Vi. So, these two rules will be applicable on exchange areas. Now, we will learn some more rules to find out exchange areas to ease the calculation of exchange areas in complicated geometries. We see that the evaluation of direct exchange area is going to be very difficult. So, we will see how much simplification we can do, what kind of rules we can follow to evaluate the direct exchange areas. The first in this is basically the Yamamoto's principle. Yamamoto's principle says that gas surface and gas volume exchange areas can be calculated for a new geometry if the gas surface and gas volume exchange areas for some old configurations are known. So, from known configuration we can calculate exchange areas for an unknown configuration. So, to demonstrate this, let us see, we have a geometry, rectangular enclosure. We have divided this enclosure into two surface zones 1 and 2. So, 1 and 2 are surface zones, and we have 4 volumes 3, 4, 5, 6. These volumes are of different dimensions. Volume 3, 4, 5, 6, they have different dimensions. Now, as per Yamamoto's principle, this S1 G4, that means direct exchange area between 1 and 4 is equal to direct exchange area between 2 and 3. Okay. Irrespective of the dimension of 3 and 4 not same, it is following the equality, that means S1 G4 is equal to S2 G3. Similarly, S1 G6 is equal to S2 G5, and the principle is also applicable to volume direct exchange areas. That means S3 G3 G6 is equal to G4 G5. So, between these two volumes and these two volumes, the direct exchange areas are same, G3 G6 and G4 G5 are same. So, this is Yamauti's principle, and this principle can be used to evaluate direct exchange areas in a typical geometry where some configuration exchange areas are known, some other configuration exchange areas can be calculated easily. So, let us do one example to demonstrate how the exchange areas can be calculated based on the principles that we have learned. We will assume a configuration of two infinite parallel plates separated by a distance L. So, this is plate 1 with area A1 and this is plate 2 with area A2, and these plates are infinite in dimension. So, in a sense A1 and A2 are also infinite. We have a finite separation distance L between the two plates, but the x dimension and the dimension in the plane of the board is infinite. Now, as per the definition, the exchange area SI/SJ is equal to double integral over surface AI and AJ, where I is equal to 1 and j is equal to 2, e power minus beta s, where beta is the extension coefficient between these two between these two plates, and cos theta I and cos theta j are normal angles. So, from this configuration we know that theta I is equal to theta j, where from theta I is basically this is let us say some small element of the plate AI, and at any element on A2 the angle made from the normal is theta. So, this theta is going to be same. Now, the way we will evaluate this, we will take an annulus of some thickness. So, let us we will take an element of thickness. So, in a sense if we look at the projected part of this plate, so we are basically considering annulus to evaluate this integral. So, what we have taken is this is the plate the annulus thickness, and we will integrate from r is equal to 0 to r is equal to infinity. So, this is how we are going to evaluate this. Now, let us write down some simplified relations basically. So, we have distance r here. So, r is basically nothing but L upon cos theta, theta I and theta j are same. Now, the area of this annulus, this area let us call this dAj. So, dAj is basically equal to the parameter of this annulus times the width of this annulus. So, this will be equal to, the parameter is going to be equal to 2 pi r sin theta, and it will be multiplied by its width. So, width is basically r d theta by cos theta. Okay. So, this is going to be the dAj, which is now coming out to be pi r square tan theta d theta. So, the area of this annulus is going to be pi r square tan theta d theta, where r is that separation distance from plate 1 to plate 2. Okay. So, we basically transform our integral, okay, and after transformation substituting for this, we get the exchange area between these two plates SS is equal to 0 to pi by 2 sin theta cos theta e power minus kappa L. Now, beta is equal to kappa, there is no scattering. So, the extension coefficient is simply equal to absorption coefficient kappa. So, kappa is the absorption coefficient, L is the separation. So, we get 2 sin theta cos theta e power minus kappa L upon cos theta d theta. So, this is the integral that we have to evaluate finally, and we can evaluate it by using the technique of change of variables. So, we put this 1 upon cos theta as t, and our equation is transformed as SS is equal to 1 to infinity to e power minus kappa L t, where we have put t is equal to 1 upon cos theta t upon t cube dt, and we have already learned what this integral equals to. This is basically the exponential integral of third order. So, this integral is basically nothing but E3 kappa L. So, the direct exchange area can be easily calculated using this approach. So, we have got the direct exchange area between these two plates as simply equal to 2 times third order exponential integral evaluated at kappa times L. Now, we have to evaluate surface to gas direct exchange area as well. So, we will see how to evaluate this surface to gas direct exchange area. We will introduce one more concept, and this concept basically says that if you have two plates, let us say we have two plates, let us say this is plate 1 and this is plate 2, okay, and the direct exchange area between these two plates is equal to SS. Now, let us say we move this plate 2 little farther, this is the new position of the plate, okay, we move it by let us say amount dx, okay, then d, the surface to surface direct exchange area is going to change. When we move the plate 2 farther away, the direct surface to surface exchange area is going to change, and it says that direct surface to surface exchange area change by a small amount dx, and this is equal to surface to gas exchange area. So, whatever change in the surface to surface exchange area happens, basically that will be equal to the surface to gas exchange area. So, what it means is whatever energy earlier was absorbed by the surface, now after the movement that energy is going into the volume. Earlier the energy was going from one surface to another, now the surface has moved further, then the change in that energy going from one surface to another will be actually going from surface to the gas. So, that is basically this principle. So, surface to gas exchange area, where dx is the distance between the initial configuration and the final configuration. So, dx is the distance the plate has moved. So, this will be equal to minus the derivative of the direct surface to surface exchange area. Now, surface to surface exchange area we have already calculated in the previous problem, 2 times exponential integral kappa times L. Now, here L we replace by x, let us say this distance is x. So, we get 2 times kappa d by d of kappa x E3 kappa x dx. So, we have to differentiate this exponential integral, and the rules or the properties of exponential integral can be exploited now. So, surface to gas exchange area, direct exchange area SG dx is simply equal to 2 times kappa exponential integral of second order E2 evaluated at kappa x and dx. So, this is basically what we have got the new trick to find out surface to gas exchange area. So, surface to gas exchange area can be calculated in terms of surface to surface exchange area by just simply differentiating the result. Now, same thing we can do for gas to gas exchange area. So, if we have 2 gas zones, let us say separated by surfaces, this is one gas and this is second gas, okay. Now, what we do is we have this is dx and this is dx prime. So, what it says is that gas to gas direct exchange area, where one gas zone is of thickness dx and another gas zone is of thickness dx prime, is equal to minus derivative of surface to gas or gas to surface direct exchange area d by dx of gs dx, okay. Now, substituting for this expression for gs from here, it becomes a double derivative, second order differential. So, we get del square ss upon del x prime dx dx prime. So, using this double derivative, we can calculate gas to gas direct exchange area as well, and this basically simplifies to, when we substitute the value of Sg dx from here, this simplifies to that surface to gas direct exchange area. This will be equal to gas direct exchange area dx prime. This will be equal to 2 times kappa square first order, because now we have differentiated twice. So, first order exponential integral evaluated at x minus x prime times kappa. So, this is the expression for the volume to volume direct exchange area between two volume zones of thickness dx and dx prime. Now, let us apply this to a configuration. Let us see how we can use this to solve for the direct exchange area. So, I have taken this configuration. We have two volume zones Z1 and G2, and we have 4 surfaces S1, S2, S3 and S4. So, 4 surfaces bounding 2 volume zones, and this is vacuum. So, there is no gas here. The distance, we can write down this distance as x12, this distance as x23 and this distance as x34. So, G1 S3 as per the definition of this G1 S3 is equal to S3. So, G1, this is the G1, S3 is equal to S3 S2 minus S3 S1, that is S3 S2 and S3 S1. So, G1 S3 is equal to S3 S2 minus S3 S1. So, summation rule on surface 3 we have applied, and this becomes G1 S3 is equal to S3 S2 minus S3 S1. Now, G1 S3 we can calculate from this relation, let us call this equation 1 and this is equation 2. So, G1 S3 we can evaluate from equation 1, and this becomes 2 times third order exponential integral kappa times x23, where x23 is the distance between plate 2 and 3, x23 minus third order exponential integral kappa times x13. Okay. So, this is how we can evaluate the volume to surface direct exchange area G1 S3. So, G1 G2 can be written as equal to G1 S3 minus G1 S4, and now what we can do is we have to write G1 S3. So, G1 S3 already evaluated. So, we substitute this value, let us call this equation 3 and this is equation 4. So, substituting the value of G1 S3 from 3 into equation 4, and we have also need to evaluate G1 S4. So, G1 S4 is simply equal to minus E3 kappa times x24 and third order exponential integral kappa x times 14. So, we have basically calculated volume to volume direct exchange area as well by simply using the rule of derivative. So, all we need is basically to evaluate surface to surface direct exchange area and surface to volume, and volume to volume direct exchange area can be calculated by just differentiating that the expression for surface to surface exchange area, and this is how we have evaluated this. So, let us call this equation 5. Okay. Now, finally, we can simplify this again using the summation rule. So, from this one, now we apply the summation rule to gas zone 1, this is zone 1, this is gas zone 2. So, we apply on zone 1. So, on zone 1 we have the summation rule G1 G1 is equal to 4 kappa 1 V1 minus G1 S1 minus G1 S2. So, with this summation rule we get 4 kappa 1 V1. Now, G1 S1 and G1 S2 are same. So, G1 S1 and G1 S2 are same because of symmetry. So, we get 4 kappa 1 V1 minus 2 G1 S1. Now, G1 S1 again from the summation rule is basically equal to A1 minus S1 S2, okay, from this zone 1. So, G1 S1 is basically equal to A1 minus S1 S2, that means all the energy from surface 1 is either going to S2 or going to volume zone 1. So, substituting this here, now our final expression becomes for G1 G1 as 4 kappa 1 x12 V1 is basically equal to x12 assuming unit depth in the plane of the board, minus 2 we assume A1 to be 1, minus 2 times exponential integral kappa x12. So, this is the expression for the direct exchange area from zone 1 to zone 1 itself, and from zone 1 to zone 2 we have calculated earlier G1 G2 and the expression is from equation 5. So, all the exchange areas, direct exchange areas we have calculated by either using the summation rule or using the differentiation method that we discussed in this lecture. So, thank you for your kind attention. In the next lecture we will discuss the Monte Carlo method for the solution of radiation problems. We will discuss how by emitting photons and tracking them in space can actually solve a problem in any complicated geometry.